The broadcast is now starting. All attendees are in listen-only mode.
Good morning, good afternoon, good evening, folks. Welcome back to another great episode of our Best Practices webinar series with 7Signal. If you could, please let us know where you're logging in from today. I see a few of you have joined early. If you'd like to, let us know if you're working remotely from home, if you're in the office. I am back in the Cleveland headquarters office, and we are joined by special guests Mike Graham today and Jim Vajda. How are you guys today?
Very good, very good. Here in Cincinnati, it's sunny and headed for 60 degrees, so very good.
See, we have the sunshine, but not it's still in the 30s kind of level. So still chilly up here, but looking forward to spring hopefully coming soon in full force. All right, we see a few of you dropping in here. We have Alan working in the office today. Thanks for joining us, Alan. We have Karsten joining us from Germany. Thank you for joining us today. Appreciate it. We have Brian working from home in Denmark. Thank you, Brian. And we have Olivier joining us from Vancouver. Thanks for joining us today. All right, so we are 7Signal, the leader in wireless experience monitoring, and we'll talk a little bit more about our story as 7Signal as we move forward here. So we've got a great topic here today, techniques for controlling and shaping RF to improve Wlan functionality. So as I said, we are joined by Mike Graham today, who will be leading us in our discussion, and of course, joined by Jim Vajda, who will be assisting and helping with the Q&A today. So looking forward to hearing from you all later in the presentation. A couple of announcements before we begin. First off, really excited about this. We announced this last week, but 7Signal has recently been awarded our 15th patent overall for advanced network performance management from any wireless device. And this is our 5th patent specifically for Mobileye. So really excited about this. We'll drop a little bit more information in the chat here if you want to read more about it. But moving forward here, we also host a product tour every single Friday at 12 noon Eastern at that link there to register. So if you haven't recently joined us for a product tour, highly suggest doing so, as there are a lot of exciting updates with, of course, Mobileye and Sapphire Eye. We also partner with CWNP for every single one of our webinars. So if you're pursuing a certification and would like CE credits for attending today, just drop us a note and we can easily send over a PDF certificate to you. We also send out a newsletter every other Wednesday morning. So some of you may have received that today. But if you aren't currently receiving that and would like to, we will drop a link in here to join that newsletter as well. And as you can see with that newsletter, we drop in a lot of relevant articles, blogs, survey questions to gauge our audience of Wi-Fi engineers in our community out there. We also post all of our slides to our Twitter account. So if you're on there, go ahead and give us a follow at 7Signal, and that will be up there later this afternoon. But if you aren't on Twitter and would still like access to the slides, no problem. All of you attending today should receive a follow-up email tomorrow with the recording and today's presentation as well. We also post the recording to our YouTube channel, so you can go ahead and watch today's broadcast there, in addition to all of our previous topics that we've covered. So go ahead and check that out. And lastly here, we've been talking about this all month. We are giving away an Oculus 2 to one special attendee who has attended several webinars this month. And that lucky person is Danae Ferguson. So congratulations, Danae. We will be reaching out to you soon to get that over to you promptly. So congratulations, and to the rest of you on the line. We really appreciate you attending our webinars every single week, and we're always doing giveaways. So stay tuned for more information there. One last announcement here. We do also have an exclusive webinar coming up at the end of this month, how the post-pandemic era will change remote working, with special guest Jeremy White, executive editor at Wired. Really looking forward to this webinar coming up here in the next couple of weeks. We will drop a registration link here in the chat as well if you want to be the first to register. Okay, a little background on 7 Signal. We were established in 2007 in Helsinki, Finland, and we are now located in lovely Cleveland, Ohio. We've hit a lot of major milestones along the way. We're really proud of the 1 billion data points that we're analyzing daily, in addition to the 5 million devices that we're monitoring daily as well. We also have over 200 customers, over 30 partners, and 15 patents, which we're really excited about, of course. So that goes to show that the technology you see from 7 Signal, you're only going to see from 7 Signal. A little background as to what makes us so different here. So if you look at our typical enterprise LAN infrastructure here on the right, you've got your Riverbed, Cisco, Aruba, AppNeta, and more that are giving you really great feedback and useful data. But we pick up where they leave off, giving you full visibility into the user experience from the outside in with our product of Mobileye, which can ultimately be installed on any mobile device from your laptops, your scanners, your pickers and scanners, as I said, workstation on wheels, and more. And Mobileye can be installed on any Mac OS, Linux, Android, or Windows device as well. We also have Sapphire Eye, which are our sensors for service level quality and RF visibility, giving you full perspective through this combination into what is occurring in your wireless network environment, which is giving you that perspective that you just can't find anywhere else. Okay, moving forward here, we do have a trivia question before we begin. So we'll go ahead and launch this poll here. And Mike, let us know how we do today. Can you guys see this question?
Yep.
Perfect. So thinking of the new Wi-Fi 6E band, what is the wavelength at about 6.5 gigahertz? So I'll let you drop in your answers here. Okay, we're gonna close this out and see how we did here, Mike. How do we do?
I guess we did okay. We had a lot of people picking the 5 gigahertz, but the answer was actually looks like we did pretty good on it. We did have a lot of people picking 1.2 inches, which is 10 gigahertz, but not too bad.
All right. Well, thank you to all of you for answering. And with that, we're going to go ahead and pass the controls over here to Mike so he can go ahead and get started with today's presentation. And while he's getting set up, I'll let Jim give a little introduction to Mike and what we're going to be talking about today.
Yeah, happy to. So Mike Graham is our sales engineer on the eastern seaboard. He's in the North Carolina area, so he's avoided the most severe weather that's struck the rest of the country, the U.S. at least, this winter. And he's going to talk a little bit about what we can do to shape and influence our coverage from the infrastructure side and different possibilities there. So you ready to go, Mike?
Yeah, I think so. Can you see my screen?
Yeah, looks good.
All right. Well, I'm going to start out talking about the AP settings that can influence the coverage area, and there really are only a couple. The first one is transmit power, and it really is just about as straightforward as it sounds. You're going to turn up the power, you get more range, and the rule is pretty simple as well. Add or remove 6 dB of transmit power, and all else being equal, that will double or halve the range. A little diagram at the bottom kind of illustrating those changes. But something that we do need to remember, especially if we start thinking about just crank it up, that a lot of client devices have a dramatically less powerful radio, both because they're usually shooting for a lower price point and because client devices often have to worry about power savings on the battery. So clients, you know, they can range from maybe 10 to 30 dBm power-wise, or 10 to 30 milliwatts rather, power-wise. So, you know, you don't want to get too crazy on the power, but if you need to go adjusting range, that plus or minus 6 dB is the key. Anything to add on that one, Jim?
No, I think that is a good range as well to use. You don't want to get a lot more than that or a lot less than that, but staying within that range is gonna kind of you know, keep you within what's reasonable of the design you have.
Yeah, I agree. That that client power range is a really reasonable place to start for access point power as well. Well, that didn't work. Oh, there we go. The other one, really, that's an access point setting is the PHY data rate, the over-the-air data rate. And, you know, we need to remember that lower PHY rates require a lot less signal strength, a lot less SNR to decode. And these lower rates give us much larger range. There's a sort of a typical sensitivity for A and G rates in the lower right corner. And kind of remember that 6 dB thing plays in there as well. If you change the data rates by 6 dB, you're going to have, or if you change the data rate so sensitivity changes by 6 dB, that's going to double or halve the range as well. But you know that it isn't quite as simple whenever you change those data rates, and particularly we're talking about removing the very lowest data rates to shrink the cell size is the usual context. The PLCP, let's see if I get this right, physical layer convergence protocol. Did I get that one, Jim?
I think so. I usually just call it the preamble, so nice job adding that on.
Anyway, the preamble and the header, which is transmitted at the beginning of every frame, is always sent at the lowest rate defined for the PHY. So if the radio supports B, which most 2.4 radios do, in fact, I think all, it's going to be sent at 1 megabit, unless it has a G only mode, which is a little different than just removing the B rates, and sometimes does break clients. And that has brought up the discussion of, you know, does it really matter, since the preamble and the header are sent at these lower data rates? Does turning off those lower data rates really matter, especially from a contention domain, shared media point of view? And just in the last few days, we had a customer, and this environment was kind of a material handling at the exit of a production, so sort of a warehousing application that used a lot of 2.4 only devices, legacy devices, and they were having not great performance. So we suggested they turn off the B rates. And if you look at the graph in the lower left corner, the orange line is their 5 gigahertz. So it was getting really good, 100 plus megabit performance, very consistently. And then way down at the bottom is their 2.4. And when we turned off the B rates, and that's all we did, we left 6 set as the lowest mandatory, you can see the truly dramatic performance increase that we saw on 2.4. They went from something like 30 megabits to something like 100. So pretty dramatic there, don't you think, Jim?
Yeah, it's a huge difference, and it's interesting too. This is measured from our Sapphire, which isn't using those rates. It's just the effect of having them present and other devices using them, and the AP using them for management traffic, which of course the Sapphire would use as well. But yeah, it can make a huge difference in performance.
I was truly a little bit surprised that it mattered so much, and yeah, you're right. The big difference wasn't so much the change in the cell size; it was lowering the overall management traffic utilization of the network. But really dramatic. And the thing that sort of surprised me is it wasn't a super dense environment either. It was originally surveyed for 2.4. kind of, warehouse basic coverage density, and it still made that much difference. So I think if you don't have to have those B rates, it's really worthwhile to turn those off. Moving on, the kind of next most obvious, and I think the most obvious way to control the coverage area is omnidirectional antennas, or is using your antennas. And we talked about omnidirectional antennas a lot in a previous webinar, so I'm not going to go into too much detail, but our good old plus or minus 6 dB comes into play again here, having and doubling the range. But do keep in mind that if you increase gain and increase range, you you definitely pay a price. There's nothing for free, and the elevation coverage, the vertical coverage, is going to decrease in proportion to the increase of the range. And Cisco has some really nice diagrams in their antenna basics presentation, which I was sorely tempted to steal, but did not. Instead, I did some of my own not so great graphics to sort of illustrate the point, with the circle being coverage from an Omni as you look down on it from the top, and then below it, coverage as you see from the side. And the proportions are really close. I kind of measured my angles and got the proportions right. So as you move up to really high gain antennas, the coverage pattern can get quite thin. And as I say, we talked about those quite a lot on our omnidirectional antenna series. But there's really no reason that you can't use high gain antennas for modern N and AC networks. Obviously, you would not want to push for large range, large coverage areas in a dense environment. But if you're really looking for basic coverage, there's really nothing wrong with putting some gain on modern access points. You have any thoughts on that one, Jim?
Yeah, the only the only gotcha to look out for is if you have really high ceilings, because you might be tempted to think, oh, I need a high gain antenna to get my signal all the way down to the floor. But if you're using an omnidirectional antenna, you may end up with even less signal on the floor because of the way the signal is focused more in the horizontal directions by that gain.
It's really easy to get all the signal up in the ceiling, and I can remember when some of the early WISP entrepreneurs were setting up systems. They would, stick up 15 or 16 dB Omni on top of a 100-foot tower and wonder why they didn't get any signal from it. And, you know, all the signal's 100 feet up in that case. So yeah, you definitely need to keep the antenna kind of close to the same plane that the users are in if you're going to go for big gain omnis.
Yeah, a normal ceiling height is perfectly fine in that case.
Oh, I couldn't find any real good graphics for this one, but you know, a couple applications where you might not use the integrated antenna, and you would want to, you know, put a little bit of gain. You know, we talked about maximizing the coverage in big open areas, particularly without the antenna being too high. You need to make sure you don't have a lot of client device density there, because as your coverage area goes up, you're obviously going to include more clients. And then really, and I think maybe this falls outside of shaping RF, but since we're sort of talking about antennas, the application that I see most for omnidirectional antennas on modern access points are the ability to remotely locate that antenna. So either an enclosure situation where you need to pull the antennas outside, or you need to locate the access point away from the users for some physical constraint. And you can use external antennas and cables and relocate those antennas wherever they need to be. Next, we're going to talk about directional antennas, and I'm kind of lumping anything that isn't an omni in that directional. So whether it's a big high gain dish or a Yagi or a little bitty patch antenna, I'm going to call it just a directional antenna. And that is probably going to be today a patch array. Could be one of the others, but by and large, the economics of these patch antennas, which I've got some examples of there, make those really good choices. Also, as you can see, these are essentially the same antenna. They're I found a website that the manufacturer had been nice enough to publish pictures of a lot of their antennas. These are all actually cut for 4 gigahertz, so between 2.4 and 5. But the principles apply, and the antenna wizards can adjust the number, the placement, the exact dimensions of these transmitting elements, the square pads on these, to really tailor the azimuth and elevation pattern to anything they want it to be. I did a little bit of virtual antenna shopping, and you know, these patch antennas, you can find them in azimuth beam widths from 10 to over 120 degrees and elevation from 10 to about 45. So, you know, you can really check 2 or 3 manufacturers and usually find an antenna that's going to be just exactly what you need. And these are available anything from, you know, really low gain, like our little single pad here, up to, you know, well over 20 dB of gain with big panels. And our 6 dB rule still is going to apply as we double the gain, or as we increase 6 dB on the gain, we'll double the range, and vice versa. Do you ever use anything other than patches, or do you see much else besides patches nowadays, Jim? Or do you think, like I do, that they're about taking over the market for antennas?
That is a good question. And off the top of my head, I can't think of it, in the last few years, seeing a design that involved anything besides omnidirectional antennas or patch antennas.
Yeah,
Even the really kind of specialty stadium designs. I can only think of seeing patch antennas in those designs these days.
yeah, I think it's really driven by the economics because these antennas, I mean, they're a printed circuit board and you expose them and etch them, and it's very little labor. Um, the PC board material is a little more expensive for antennas, but if you think about the amount of labor that goes into something like a Yagi, where you've got mechanical construction, skilled labor to put those together, I think it's really driven by the economics more than anything else. And like I said, you can find just about any um, beam pattern, any azimuth and elevation that you look for out there. I was kind of amazed. I haven't done a lot of antenna shopping lately, and there's a lot of choices out there. So a few applications for these, and certainly by no means an exhaustive list, but I had to find a reason to include this picture again. It was in one of my other presentations, and I liked it so much that I thought I would include it as sort of one of the classics where you do tend to use directional antennas. And warehouse aisles is one of the very, very first. And it's a difficult situation otherwise. High bay racking, it's really hard to get the signal down to the ground level whenever you've got 40 or 60 foot racks and your access point is above you. It's also hard to get up there and install them and maintain them. And we have really good propagation along the aisles, down the length of them, and usually, depending on the product, pretty terrible propagation across them. So it's a natural fit for really pretty big gain antennas in a lot of cases, firing down those aisles. Anything to add on that one, Jim?
Yeah, that's a really classic use case for directional patch antennas, and it's really one of the best ways to handle a warehouse design. I think that's become so common now that some antenna manufacturers have warehouse specific patch antennas that are really designed to take into account the geometry of the area they're operating in.
Yeah, it is a major application for them. The other one, interference mitigation, which I don't actually hear talked about very much. Some in the kind of point-to-point outdoor realm, but it really applies for more traditional Wi-Fi as well. And my very basic diagram here on the bottom, where we have an interferer on the left in red, an AP in the middle, and a client device over on the right side in green. And by using a directional antenna, you point the back of the antenna, the null of the antenna at the interferer, and it's going to greatly reduce how clearly the access point hears that interferer, and hopefully you'll bring it down to the point where the access point won't try to do an energy detect defer to it or anything like that. And of course, the client device benefits as well, since it's got the AP closer than the interferer, with an inverse square law. Distance is everything in radio. And as I say, I don't hear this one talked about a whole lot. How about you, Jim?
Yeah, it's sort of related to the idea that a directional antenna will help you focus all the energy, all the RF from an AP in the area you want it, and not in areas that you don't want it, which could also mean,
Yeah.
On the receive side, the AP is unaware of transmitters over in those areas you're not concerned with that could be causing interference and contention.
Yeah, usually with directional antennas, or really any antenna, you think in terms of where is the signal, not where is the signal not. And this is sort of that case of using the anti-coverage where you've got negative gain and pointing that at an interferer. The others, we want to, when you've got an area that's not close to a structure that you need to get coverage in, on the left, we've got actually, but it's a high school, and they designated a parking lot that they wanted Wi-Fi coverage available in. And it's no way to get out there easily. And, a big sector or a big directional antenna on the corner of the building firing out at that lot really provided very adequate coverage. And I happen to know on this particular application, the alternative suggested involved, trenching and jackhammers and repaving, and was really an expensive solution compared to mounting an antenna on the outside of the building. And on the right, we have a photograph of Jim's house and his pool area. And I think you're covering that one with directional on the back of the house, right, Jim?
Well, it is sunny today in Ohio, but we don't have palm trees and beautiful mountains and crystal clear water in the pool. So that would be a good spot for external antenna, though, for sure.
Yeah, because you've got to have Wi-Fi in the hot tub.
You must.
Move on a little bit, and I'll talk about using the building structure to shape coverage. And the first thing I thought of is hallways, and usually we think of them as something to avoid. They tend to tunnel the signal down the hall very effectively. Sometimes you can get really tremendous range sometimes. But the reason that we usually avoid them these days, anyway, is usually we're trying to cover the rooms off of the hall. And so we avoid those hallways where you get that tunnel effect. That said, if the application is covering that hallway, certainly you can use that long waveguide-like propagation to your advantage. It's really depending on what you want to do. And isn't that a great hallway?
Yeah, you can almost feel the waveguide going down that hall, which actually might not be a bad thing, right? If there's only, maybe one AP that's getting affected by that, and you've got clients that are mobile, like a voice over Wi-Fi handset, and you prefer it not to have to roam, unnecessarily, then you could use that to your advantage. Now, if you have APs lined up, on the ceiling in the hall going down that hall, they will all be, unfortunately, subject to that waveguide effect. And then you'll just have this huge pileup of co-channel interference in the hall. It's going to be hard to deal with.
That's right. So, once again, you have to kind of pay attention to what your needs are. In this particular case, I don't actually think they have coverage in the rooms off to the side, so it might be a good thing. The other one is, and you see this in tower buildings a lot, you have a really heavily built central core. It's a major part of the structure of the building. It's going to have your elevator shafts, your restrooms, utilities, stairways, and they all tend to be very heavily built, heavily reinforced, and really poor penetration, which, you know, it's great for channel reuse. You can use APs on the same channel on one side of the core versus the other. They're usually not going to hear each other. So taking advantage of that is great. And I kind of illustrated in the green ring there, almost the sweet spot usually for installing access points in one of these buildings. And it's something I wanted to slip into another presentation and never found a place to talk about it, so I'm putting it in here. You'll notice the four little red squares at the inside corners of that core. And those are really good places to avoid putting an access point. And the reason is you're truly setting yourself up for a hidden node issue there. And if you see the two C's that I have in red where client devices are, they could easily both be connected to an access point in that corner there and not be able to hear each other, and therefore potentially transmit on top of each other, interfere with each other at the access point, and push up your retransmissions, which are never a good idea. So that's sort of a case of the core working against you, and that you do have to remember that not only can access points not hear each other through those cores, clients can't either. And because it is a shared medium, really all the devices need to be able to hear each other in a cell. What do you think about that one, Jim?
Yeah, that's a very good point. And sometimes there's a little bit of tension between trying to avoid situations where you have hidden nodes, but also trying to design for graceful roaming. So what I mean by that is you want a client that's mobile to hear the next AP and be aware of it long before it needs to roam. So that by the time it gets around that corner, which is going to create an RF shadow, it's aware of the AP that's there that it needs to roam to, and it's not panic roaming where it's sort of, uh-oh, my signal strength all of a sudden dropped off a cliff and I don't know where to go. I better start scanning really quickly. I'm going to start experiencing packet loss until this is sorted out. So there's sometimes some tension there between accepting some degree of potential for hidden nodes and also providing for graceful roaming. But it all goes down to the requirements for the design, really.
Yeah, it does, and you do have to be aware that you need another access point visible, from at least the border areas of each access point's coverage area. Although after spending a little bit of time in Mobileye looking at the way clients roam, I'm thinking you're attributing too much intelligence to them, but I don't know.
Yeah, it's always a mixed bag, isn't
it? And I think that's it for me.
Good. Well, Mike, we got some good questions that came in from the audience. This is always a topic, these kind of layer one RF issues are always popular and generate good questions. Derek says, have you seen any issues with high gain antenna use in regards to asymmetrical signal strength bidirectionally with clients? And I won't mention the vendor here, but he does name a vendor that says they mention this frequently, and he wonders what real world experience says. So I think we have some misconception here about antenna reciprocity.
Yeah, and it is really a basic characteristic of basically all antennas. There are a few designs that it doesn't apply to, that what they do for transmit, they do for receive. So if you're getting transmit gain to a client, you're getting receive gain as well. So unlike where maybe you jack up an access point's power and you have a very unbalanced link because you have a power discrepancy, an antenna isn't going to give you that, because it adds gain on the receive side as well as the transmit side.
Yeah, so as long as they're both putting out somewhere near the same amount of power, the link should be balanced. Yeah.
Yep.
Question.
You know, just to add a little bit, and I won't mention a manufacturer either, but at least one or two of the major manufacturers, their automated power control algorithms are really biased towards turning down AP power. So we frequently actually see, and I think it's odd, but we see the situation where APs are hearing the clients just fine, but the clients can't hear the APs. So we actually find much higher retry rates on the AP side and lower data rates down than up. So if you're going to let the automated power control run wild, you may see that, and I definitely suggest setting minimum and maximum power levels for APs. And I think I interrupted you, Jim.
Yeah, that's okay. Nolan says, graphics always make it seem like there's no signal directly beneath an omnidirectional antenna. How severe is that lack of signal?
Not very severe. Usually the inverse square law, distance versus power, really is such a strong determiner of signal strength. Even if you're in a pretty deep null, if you're close to the AP, you're going to get reasonable signal. I've only ever seen it a problem standing under really high gain antennas at high elevations. Anything kind of indoorsy doesn't seem to be much of a problem to me. Have you seen that, Jim?
No, only really sort of looking at the extremes of the coverage from an AP, maybe 2 or 3 floors away, you might notice a real difference directly beneath the AP, but then you're all quite a bit away from where that the clients are operating for that AP.
Yeah, inverse square distance rules,
Yeah. So yeah, and the inverse square law is a good transition. I've had a lot of questions seeking clarity about essentially the rule of 3 dB, rules of thumb around 3 dB and 6 dB. Maybe you could summarize that, Mike.
Well, 3 dB is important because that represents half or double power. If you increase an output by 3 dB, then you're going to increase the output double. So 10 milliwatts becomes 20, or 20 becomes 40. I think the 6 dB rule is probably more important because that relates to the range. Increasing or decreasing power by 6 dB halves or doubles the range. So those are the basic rules there, I think.
Yeah, exactly. We're really talking about different phenomenon. The doubling of power and moving up 3 dB is just a way of kind of simplifying or getting a feel for the way decibels move logarithmically versus the way power needs to increase exponentially to keep up. But the 6 dB rule is totally different. It's about getting a feel for the way signal strength degrades over distance, and how we can express that, the effects of free space path loss, which is of course a version of is the underlying math is the inverse square law that's affecting that.
Right.
So different phenomena. And I think, Kelsey, we're right on time, so I think we should probably wrap it up.
All right. Well, thank you to all of you for dropping those questions in there. Really great discussion today. We love hearing from the audience when we go through these presentations. And a huge thank you to Mike and Jim for walking us through this today. Thanks again. All right. And thank you to also everyone on the line today. We really appreciate you spending some time with us during your workday to dive into this. And as always, we hope to see you at next week's webinar. So thanks, everyone. Have a great day. Bye, Jim. Bye, Mike.
Goodbye.
Thanks, guys.